This video is on the difference between mass and weight and inertia. The objectives for this video are as follows. When you're done watching this, you should be able to explain the difference between mass and weight, calculate an object's weight in newtons if you know its mass, and calculate an object's mass in kilograms if you know its weight in newtons. And then finally, we're going to review about what it means for two quantities to be directly proportional or inversely proportional. Now, we talked about the difference between mass and weight before in our last unit about forces, but let's review it. A lot of people use the terms mass and weight interchangeably, but to a physicist that makes them really cringe, because mass and weight are not the same. Mass is how much matter is in an object, or how much chemical stuff is in an object, and weight is actually a force on that stuff, on that matter. And the force is actually gravity pulling down on that mass. Another way you can think about this is that mass is a property within an object. It depends on how much stuff is in that object. But weight is an outside force on the object. So weight depends more on the force that's pulling on the outside of the object, and mass is how much stuff is within the object. And weight actually depends on mass, because gravity can't pull on anything if there's no stuff to pull on. So here's a slide that we had before that hopefully helps you understand a difference between mass and weight. And that's comparing both on the Earth versus on the Moon. And this example uses a bag of flour that has a mass of 2.3 kilograms. So it has 2.3 kilograms of stuff in it. Now, how you determine the weight of this is you would use a force meter. And hopefully you're a little more familiar with those now as well. When you hang this bag of flour from the force meter, you can see that it has a weight of 22.2 newtons on Earth. If you took this whole system up to Mars and hung that bag of flour on this force meter, now the bag of flour would have a weight of 3.6 newtons, even though it still has a mass of 2.3 kilograms. So the amount of chemical stuff hasn't changed in the flour. What's changed is the pull of gravity on that stuff. Since the moon is smaller than the Earth, it has less gravitational pull, and that's why a bag of flour has less weight on the moon than it does on Earth. And you can see that the weight of something would change depending on which planet or which body it's on. So for example, all of these have the same mass of a person, 63.5 kilograms. The atoms that make up that person don't change. But if you place that person on different planets, or the moon or the sun, their weight would change a lot. So somebody that weighs 140 pounds on Earth would weigh a lot more on Jupiter and a lot more still on the sun. So keep in mind that the unit that we're going to use for force or weight is going to be in newtons, and an important unit of mass that we're going to be using is kilograms. Now I want to go back to that bag of flour demonstration. We said that that bag of flour had a mass of 2.3 kilograms. And we said that that mass of 2.3 kilograms led to a weight of 22.2 newtons. So this makes me ask the question, how many newtons equal 1 kilogram? Well, let's look and see. If you look at these two numbers, 2.3 kilograms and 22.2 newtons, and think about what that relationship is, it's almost 1 kilogram equals 10 newtons. And that's what I want you to notice. And that's going to be an important value for us. 1 kilogram equals 10 newtons. Now, how we can write this as a formula is with this. W equals mg, where W is the weight. And what are the units for weight? That's right, newtons. Hopefully you didn't just say that out loud. M is the mass. Now here's the trick about this one. Normally when we talk about mass, we think about grams. But in this case, the mass has to be in kilograms. And here's our old friend, little g again. And what's little g? Remember, little g. Little g is the acceleration due to gravity, and it's a constant, so that number stays the same. And hopefully you remember what that is, and it's 10, and the units for that are meters per second squared. So with this formula, we can convert a mass in kilograms to a weight in newtons, or vice versa. Now this 10 meters per second squared is the acceleration due to gravity on Earth. Depending on which planet you're on, that would change. So let's do an example problem. If an object has a mass of 5 kilograms, what is its weight? Whenever you approach a problem, think about what is it asking for, and go ahead and circle that. So this one says, what is its weight? And then think about what's given, and maybe underline that or put a box around it. So in this case, an object has a mass of 5 kilograms. Even right next to there, what's being asked? A mass of 5 kilograms, that's M, and weight is big W. So let's go ahead and plug this in. We don't know what weight is, so we're going to leave that as a W, but we do know that the mass is 5 kilograms, and we know that G is 10 meters per second squared. So if we multiply this together, what we get is 50, and the units would be kilograms meters per second squared, and that's actually what newtons really means. So this weight is 50 newtons. Let's try another one. In this example, an object has a weight of 5 newtons, and it's asking, what is its mass? So 5 newtons is the weight, and this is asking, what's the mass? Let's plug in what we know. The weight is 5 newtons. We don't know the mass, so we'll leave that, and little g is 10 meters per second squared. So if we go ahead and put all of that together, what we'd get, I'm going to throw out the units for right now, just to make this a little bit easier to look at. And then if we divide both sides by 10, what we'd get is 0.5 equals m. And remember, m stands for mass, so our units should be kilograms. So by looking at this formula, W equals m times g, weight equals mass times the acceleration due to gravity, we can see that weight and mass are directly proportional. Now some of you guys might know what that means, but for some of you that might be really confusing. So let's review what this means. The two terms that we need to know to determine the relationship between two quantities are going to be directly proportional and inversely proportional. So what directly proportional means is when one quantity increases, so does the other. So when quantity A goes up, quantity B goes up. Something is also directly proportional when one quantity goes down and the other quantity goes down. So when quantity A goes down, quantity B also goes down. Now with inversely proportional, what happens is when one quantity increases, the other decreases. So when A goes up, B goes down. And when one quantity decreases, the other quantity increases. So I'm sure you can think of a lot of examples of this. For example, the more you study, the higher your test score. So studying and test scores are directly proportional. You could also say that the less you study, the lower your test score. Those would be directly proportional also. An example of inversely proportional would be the more you study, the less time you have for video games. You could also say the less time you study, the more time you have for video games. So the amount of time you spend studying and the amount of time you have to play video games are inversely proportional. So mathematically, how you'd express this for weight and mass being directly proportional is just like this. How can you tell that when weight goes up, mass also goes up? Well, let's just do a quick problem. Let's just suppose that you have a weight of 1 newton. What's the mass? Well, it's this. So if you have a weight of 1 Newton and we multiply this through, that's supposed to be a times, mass equals 1 over 10. So let's make weight go up to 2 newtons. Mass times 10 meters per second squared. And if you divide this out, mass is equal to 2 over 10. And the units on these would both be kilograms. So from here to here, what's happened to the weight? The weight has increased. And when you go through and solve, what's happened to the mass? The mass has gone from 1/10 to 2/10. So the mass has also increased. These are directly proportional, and this mathematically proves it. To relate this back to Newton's laws, I want to talk about how mass and inertia are directly proportional. And to do this, I'd like to use a couple of examples. Here's a question for you. Which object will require a greater force to move? A 200 kilogram object or a 1,000 kilogram object? Hopefully you said a 1,000 kilogram object. You'd have to push that 1,000 kilogram object a lot harder to get it to move. You'd have to apply a greater force to it compared to the 200 kilogram object. Why is that? Because this 1,000 kilogram object has more inertia. Remember what inertia is. It's the property of something. It's a property of something, and it says that this object is going to want to remain at rest more than this object. Here's another question. Which object will require less time to stop moving? A 200 kilogram car moving at 6 meters per second, or a 1,000 kilogram car moving at 6 meters per second. So I'm just going to represent these cars as boxes. This one's 200 kilograms, and this one's 1,000 kilograms. And if they're both moving at 6 meters per second, which one's going to take longer to stop? The one that has more mass. This one's going to take longer to stop because it has more inertia. It's going to have a greater tendency to keep moving than the 200 kilogram object.